Have you ever stopped to wonder how the sun's energy, just this incredible power, travels millions and millions of miles through, well, nothing, through empty space to warm us up here on Earth?
Or maybe something a bit closer to home, like why your car gets unbelievably hot on a sunny day,
Yeah.
even when the windows are rolled up tight.
Yeah, it becomes an oven. These things, they hint at something really different about heat transfer, don't they? Something beyond what we might usually think about.
Absolutely. It shapes so much around us, from how your coffee cools down to the Earth's climate itself.
So today we're doing a deep dive into thermal radiation. Now, this isn't conduction, heat transfer by direct touch.
Right, like shaking hands.
And it's not convection either, that movement of warm fluids like air or water currents. Radiation is, well, the sources say characteristically different.
That's a good way to put it. And to really get our heads around this invisible energy, we've looked at some comprehensive textbook material. It lays out the fundamental physics and some really cool practical examples.
Our goal here isn't just to read definitions. We want to cut through the technical stuff, pull out the really key ideas so you walk away actually getting it.
Exactly. Those aha moments when you suddenly see how this invisible energy is working all around us.
Okay, so we know conduction needs physical contact. Convection needs a fluid, something to move the heat around. But radiation, what's its trick? How does it work without either of those?
Well, its superpower, if you like, is that it does not require a material medium at all. That's the absolute game changer.
No medium needed.
None. Think about the sun's heat reaching us. It's crossing the vacuum of space. Radiation's the only way heat can do that.
Okay, that makes sense for space.
But here's something maybe even more surprising. Radiation can happen between two objects even if the stuff between them is colder than both.
Wait, how does that work?
Imagine sunlight streaming through really cold air high up in the atmosphere to warm the ground. Or think about a greenhouse. It gets warm inside on a cool day, right? The sunlight isn't really heating the cold air or the cool glass first. It's just passing through them, carrying the energy directly to the surfaces inside.
That's pretty wild. So if it doesn't need a medium, where's this energy actually coming from? Feels like we need some basic physics here.
Oh, absolutely. It goes back to James Clerk Maxwell back in 1864. He had this brilliant idea that accelerating electric charges actually create these ripples of electric and magnetic fields.
The electromagnetic waves.
Exactly, electromagnetic waves. And then Heinrich Hertz, a bit later in 1887, he actually proved they existed experimentally. And the kicker, all these waves, whether it's visible light or heat radiation, they all travel at the speed of light.
Which is just mind-bogglingly fast.
Insanely fast, like around the Earth more than 7 times in a single second.
Wow. Okay, so they're super fast. What makes one wave different from another? What are their, properties?
They're defined by their frequency and their wavelength. And these two are inversely proportional. So longer wavelength means lower frequency, shorter wavelength means higher frequency. Simple as that.
Got it.
We usually measure the wavelength in micrometers, or microns, for this kind of radiation. Then fast forward to 1900, Max Planck comes along with his quantum theory.
Ah, Planck. This is where photons come in, right?
Precisely. He suggested that this electromagnetic energy also behaves like it's made of tiny packets, discrete bundles of energy called photons, or quanta.
Okay.
And here's the fascinating part. The energy of a single photon is inversely proportional to its wavelength. Shorter wavelength means higher energy per photon.
Which explains why some types of radiation are dangerous.
Exactly. Things like gamma rays and X-rays have very short wavelengths, so each of their photons carries a huge amount of energy. That's why they can be so destructive to living tissue. They just pack a massive punch.
Okay, so the whole electromagnetic spectrum is huge, from radio waves all the way up to gamma rays. But we're focusing on thermal radiation. Where does that fit?
Thermal radiation occupies a specific slice of that spectrum, roughly from 0.1 to 100 micrometers. And what's really fundamental about it is where it comes from.
Which is?
It's emitted constantly by all matter that has a temperature above absolute zero. So basically everything.
Everything. My desk, this microphone.
Yep. Your desk, the walls, you, me. Anything with any heat energy at all. It's caused by the constant jiggling and energy transitions of molecules, atoms, electrons. And the hotter something is, the more radiation it emits.
So we're all just constantly radiating energy at each other.
We are constantly emitting and absorbing thermal radiation. It's happening all the time. Invisibly.
Right, invisibly, because the light we see is just a tiny part of this, isn't it?
A really tiny part. Visible light, the colors we see, that's only between about 0.40 and 0.76 micrometers. It's a sliver.
So when I see a red shirt, it's not actually glowing red hot.
Huh, no, definitely not. Unless it's like over 1,000 Kelvin hot. Otherwise, its color comes from how it reflects and absorbs the light that's hitting it. Your red shirt looks red because it's reflecting the red part of the ambient light and absorbing the other colors.
Okay, that makes sense. What about the parts we can't see? Infrared, UV?
Right. So things at everyday room temperature, like us, mostly emit in the infrared IR region. That's from about 0.76 up to 100 micrometers. You need something to get pretty hot, like above 800 Kelvin, maybe 1,000 Kelvin, before you start seeing a faint red glow.
Like an electric stove burner.
Exactly. Or a light bulb filament, which gets way hotter, maybe 2,000 Kelvin or more, so it glows brightly in the visible spectrum. Then on the other side, at shorter wavelengths, you have ultraviolet, UV radiation from 0.01 to 0.40 micrometers.
The dangerous stuff.
Yes, that's the stuff that causes sunburn. Luckily, our ozone layer up in the atmosphere absorbs most of the really harmful UV from the sun. That's why protecting the ozone layer is so critical.
Makes sense. And microwaves, like in a microwave oven, is that radiation too?
It is, yeah, but it's a different part of the spectrum again. Much longer wavelengths, like 100 to 100,000 micrometers or so. Microwave ovens work because those specific wavelengths are really good at being absorbed by water molecules in food.
Ah, so they make the water molecules vibrate like crazy.
Exactly. And that vibration energy turns directly into heat, cooking the food from the inside out, essentially.
Yeah.
And one last point. For things that aren't transparent, like a block of wood or metal, we generally consider thermal radiation just a surface thing, meaning the radiation comes off the surface. Any radiation generated inside the material gets absorbed before it can get out. So emission and absorption happen right at the boundary.
Okay, so real objects, they absorb some radiation, they reflect some, they emit their own based on temperature. It seems really complicated. How do scientists even start to model this? Is there like a perfect ideal case?
There is, and it's absolutely essential for understanding the real world. We call it the black body. Think of it as a theoretical perfect radiator.
Perfect.
It's a perfect emitter and a perfect absorber. At any given temperature and wavelength, no real object can possibly emit more radiation than a black body. And, importantly, it absorbs all radiation that hits it. Doesn't matter the wavelength, doesn't matter the direction, it just sucks it all in.
All of it. No reflection.
None. And when it emits, it does so perfectly uniformly in all directions. It's the ultimate standard.
Okay, that sounds very theoretical. Can we picture something that behaves like that in the real world or close to it?
Actually, yes. The classic example is a large hollow cavity. Imagine a sphere kept at a uniform temperature with just a tiny, tiny hole in it.
A little pinhole.
Yeah. Any radiation from the outside that happens to go into that hole bounces around the inside. It gets reflected and absorbed over and over again. The chance of it finding its way back out that tiny hole is almost zero. So the hole acts like a perfect absorber.
Okay, I can see that.
And conversely, the radiation that streams out of that hole, coming from the heated walls inside the cavity, that radiation behaves exactly like it's coming from a perfect black body, perfectly emitted, perfectly diffuse, regardless of what the cavity walls themselves are actually made of. It's a clever way to create a physical reference.
Right, a benchmark. So if this black body is the ideal, how much energy does it actually emit? Are there laws for this?
Oh, yes. The first big one is the Stefan-Boltzmann law. This gives you the total energy emitted per unit area by a black body. We call this the total black body emissive power, EB.
Okay. And the law says?
It says EB is equal to a constant sigma, the Stefan-Boltzmann constant times the absolute temperature raised to the fourth power. So AD.
The fourth power.
Yes, and that's the crucial part, the fourth power of absolute temperature. It means that even a small increase in temperature leads to a huge increase in the amount of radiation pouring out.
Wow. Can you give us a sense of scale, like an example?
Sure. Let's take a sphere, maybe 20 centimeters across, so not huge, heat it up to 800 Kelvin. Now that's hot, but it wouldn't even be glowing visibly red yet.
Okay.
That sphere would be radiating over 23,000 watts for every square meter of its surface. Just think about that. In only 5 minutes, it would lose about 875 kilojoules of energy.
Which is how much in practical terms?
That's enough energy to take 20 kilograms of water, that's quite a lot of water, from freezing point, 0 degrees C, all the way up to boiling 100 degrees C.
All from that fairly small, not even glowing ball. That's incredible.
That really shows the power of that T to the fourth relationship.
Okay, so that's the total energy. But what about the different wavelengths, the different colors of radiation? Does a black body just blast everything out equally?
No, it doesn't. And for that, we need Planck's law. Max Planck figured this out around 1900, a huge breakthrough. His law gives us the spectral blackbody emissive power. It tells us exactly how much energy a blackbody emits at each specific wavelength for a given temperature.
So it breaks down the total into its components.
Exactly. And when you plot Planck's law, you get these characteristic curves. They show a few really important things. First, the emission happens over a continuous range of wavelengths. It starts low, rises to a peak, and then falls off again at longer wavelengths.
Okay, a continuous curve.
Second, if you increase the temperature, the curve moves up, meaning at any wavelength, a hotter blackbody emits more radiation than a cooler one.
That makes sense. Hotter means more energy overall.
Right. But here's the really cool part, the third insight. As the temperature goes up, the peak of that curve shifts towards shorter wavelengths.
Ah, so that's why things change color when they get hotter.
Precisely. That explains why, say, an electric heater element first glows a dull red around maybe 1,000 Kelvin. Then as it gets hotter, it gets brighter red. And eventually, if it gets hot enough, maybe 1,500 Kelvin, it looks white hot.
Because the peak is moving into the visible range and spreading across it.
Exactly. It's emitting more and more strongly across the entire visible spectrum. And think about the sun. Its surface is about 580 Kelvin. Where does its emission peak?
Right in the visible spectrum.
Bang on. Right around 0.5 micrometers, smack in the middle of the visible range. It's almost like our eyes evolved to be most sensitive to the peak output of our star.
That's amazing.
And conversely, something at room temperature, like 298 Kelvin, its peak emission is way out in the infrared, around 9.7 micrometers. That's why we don't glow in the dark visibly.
But infrared cameras can see us.
They sure can, or rattlesnakes with their heat-sensing pits. This shift of the peak wavelengths with temperature is described by Wien's displacement law. It gives you a simple formula to find that peak wavelength for any temperature.
Okay, so we have the total energy, and we know how it's distributed by wavelength. What if we only care about a specific band of wavelengths? Like how much of the sun's energy is actually visible light, specifically?
Yeah, good question. We often need to know the energy within a certain range, not just the total or the peak. For that, there's a handy tool called the blackbody radiation function, often denoted Flaunfu.
Okay, what does that do?
Think of it as a percentage, or a fraction. It tells you what fraction of the total blackbody radiation is emitted between zero wavelength and some specific wavelength lambda. It's basically the area under Planck's curve up to that point, divided by the total area.
So it's like a running total?
Sort of, yeah. The great thing is, while integrating Planck's law is mathematically messy, these lambda values are calculated and available in tables or software. So if you want the fraction of energy between two wavelengths, say 1 and La2, you just look up Fu2 and Fu1 and subtract them. Easy.
That sounds really useful. Does it show us anything interesting in practice?
Oh, definitely. Let's use it to compare the sun to an old-fashioned incandescent light bulb, just in terms of making light.
Okay.
The sun, at 5780 Kelvin, emits about 42.6% of its total energy in the visible spectrum. That's pretty efficient as a light source.
Yeah, nearly half its energy is light, we can see.
Now, take an incandescent bulb. Its filament is maybe around 2800 Kelvin. Using the same blackbody function, we find it emits only about 8.7% of its energy as visible light.
Wow, less than 10%.
Exactly. The vast majority of its energy, over 90%, is just wasted as invisible infrared heat. That's why those bulbs get so hot, and why they're incredibly inefficient for lighting. It perfectly explains why we've moved to things like fluorescent lights and LEDs, which are much, much better at converting electricity into visible light rather than just heat.
Right, so black bodies are the ideal. But radiation in the real world, it's directional, isn't it? It doesn't just spread out evenly from a point source. How do we account for where the radiation is going or coming from?
That's a crucial point. We need to talk about radiation intensity.
Okay.
Intensity is the measure that tells us how much radiative energy is flowing per unit area, but also within a specific direction and within a specific range of wavelengths. It's a more detailed quantity than just emissive power.
Direction. How do we define direction in 3D space for radiation?
We use the concept of a solid angle. Think of it like a cone spreading out from a point. Instead of measuring angles on a flat plane in radians, we measure these 3D cones in steradians. A whole sphere covers 4 steradians. A hemisphere covers 2 steradians.
Okay, like a slice of the view from a point.
Exactly. And using intensity and solid angles, we can precisely calculate how radiation travels between surfaces. We also define a few other key terms. Emissive power, E, is the total radiation emitted from a surface per unit area. Radiation G is the total radiation incident on or hitting a surface per unit area from all directions. And radiancity, J, is the total radiation leaving a surface per unit area that includes both what it emits itself and what it reflects from irradiation hitting it.
Emitted, incident, leaving. Got it.
And for ideal surfaces, like black bodies, which emit diffusely, meaning the intensity is the same in all directions, the relationship between emissive power and intensity simplifies nicely. E just equals times I.
Okay, so intensity handles the direction. Now back to real surfaces. They aren't black bodies. How do we describe how real materials emit radiation?
We use a property called emissivity. It's
Yeah.
straightforward. Emissivity is the ratio of the radiation actually emitted by a real surface at a certain temperature compared to the radiation that would be emitted by a perfect black body at the exact same temperature.
So it's a fraction between 0 and 1.
Exactly. A black body has an emissivity of 1. A perfect reflector would have an emissivity of 0. Real objects fall somewhere in between. And here's the catch. Emissivity isn't usually a single simple number
Oh, why not?
because it can depend on the temperature of the surface, the specific wavelength of radiation you're looking at, and even the direction you're measuring from.
Wow, that sounds complicated.
It can be. That's why we often talk about different kinds of emissivity: spectral at one wavelength, total across all wavelengths, directional in one direction, hemispherical, averaged over all directions. For practical purposes, though, engineers often make simplifying assumptions,
Like what?
like assuming the surface is diffuse, meaning its emissivity is the same in all directions, or assuming it's gray, meaning its emissivity is constant across all wavelengths. These make the calculations much more manageable, even if they aren't perfectly accurate for all materials.
Okay. Are there general rules, like what kinds of materials have high or low emissivity?
Yeah, definitely. As a general trend, smooth, polished metals tend to have very low emissivities. Think of shiny aluminum foil that reflects heat well because it doesn't emit it well. On the other hand, nonmetals, things like ceramics, plastics, organic materials, paint, they usually have quite high emissivities, often 0.8 or 0.9.
So metals are poor emitters, nonmetals are good emitters.
Generally, yes. But things like oxidation can make a big difference. A rusty or oxidized metal surface will have a much higher emissivity than a shiny, clean one.
Interesting. Okay, that's emission, what the surface sends out. What about radiation that hits the surface? What happens then?
Right, the irradiation G hitting the surface. 3 things can happen to that incoming energy. Some fraction of it can be absorbed by the material, turning into internal energy or heat. We call this fraction the absorptivity.
Okay, absorbed, alpha,
Some fraction can be reflected off the surface. That's the reflectivity, rho.
reflected, rho.
And if the material is semi-transparent, like glass or some plastics, some fraction can pass right through it. That's the transmissivity.
Absorbed, reflected, transmitted, alpha, rho, tau.
And because energy has to be conserved, the sum of these 3 fractions must always equal 1. So Al plus rho plus Al plus 1. That's fundamental.
What about things that aren't transparent, like most solids?
For opaque materials, the transmissivity is essentially 0. Nothing gets through. So the equation simplifies nicely, Al plus 1. Whatever isn't reflected must be absorbed, and vice versa.
Makes sense. And reflection itself, is it always like a mirror?
Good question. No. Reflection can be specular, which is mirror-like. The angle of reflection equals the angle of incidence. This happens on very smooth surfaces relative to the wavelength of the radiation.
Like polished metal.
Exactly. Or it can be diffuse. This happens on rougher surfaces. The incoming radiation hits the surface and bounces off pretty much equally in all directions, regardless of the angle it came in at. Most nonmetallic surfaces reflect diffusely.
Okay. Now you mentioned earlier that how something absorbs radiation can depend on the source. Can we dive into that a bit more? That seemed important.
Yes, absolutely crucial. Absorptivity isn't just a property of the surface itself. It also depends heavily on the wavelength distribution of the incoming radiation, which, remember from Planck's law, depends on the temperature of the source emitting that radiation.
Okay, so the same surface can absorb differently depending on what's shining on it.
Precisely. Let's take your concrete roof again. For incoming sunlight, which comes from a source at roughly 5780 Kelvin, peaking in the visible spectrum, the concrete might have an absorptivity of maybe 0.6. It absorbs 60% of the solar energy.
Right.
But now consider radiation coming from the surrounding environment, like trees, other buildings, the ground, which are all much cooler, maybe around 300 Kelvin. Their radiation peaks way out in the infrared. For that long wavelength radiation, the same concrete roof might have a much higher absorptivity, say 1.9. It absorbs 90% of that infrared energy.
Wow. So it treats solar heat and ambient heat very differently.
Totally differently. This is why white paint is great for keeping things cool in the sun. It has a low solar absorptivity. It reflect sunlight well, but often have a high absorptivity and emissivity in the infrared, allowing it to radiate away any heat it does absorb.
That is counterintuitive, but makes sense now.
Yeah.
Okay, so we have emissivity, how well it emits, and absorptivity, how well it absorbs. They seem related. Is there a simple connection?
There is indeed a very elegant and powerful one, thanks to Gustav Kirchhoff back in 1860. It's Kirchhoff's law.
Okay, what does it say?
In its most useful form, it states that the total hemispherical emissivity of a surface at a temperature T is equal to its total hemispherical absorptivity for radiation coming from a black body at that same temperature T. So essentially, DTE equals...
Emissivity equals absorptivity at the same temperature.
Yes, that at the same temperature caveat is important. It means if a surface is good at emitting radiation at a certain temperature, it's also good at absorbing radiation from a source at that same temperature.
How does that help in practice?
It simplifies things immensely. Often, it's easier to measure or find data for one property, say emissivity. Kirchhoff's law then lets you know the absorptivity under those specific conditions, or vice versa. It links the two properties together.
Can you give a concrete example of using this?
Yeah, let's go back to that factory conveyor belt with hot parts. Remember wanting to make sure they're cool enough to handle, say, below 45 degrees C.
Right, preventing burns.
You could use a device called a radiometer. It doesn't touch the part. It just measures the radiation coming off it, the radiosity. Now, if you know the emissivity of the part's surface material at the expected temperatures, you can use the measured radiation and the Stefan Boltzmann law, adjusted by emissivity, to calculate the surface temperature very accurately.
Ah, so you measure what it's emitting to find its temperature.
Exactly. But sometimes, especially if the part isn't super hot or the surroundings are also radiating, the measurement gets complicated. You might measure the irradiation hitting the part from the environment too. If you know the part's temperature should be near the environment's temperature, you can use Kirchhoff's law to help disentangle the emitted radiation from the reflected radiation, ultimately still getting an accurate temperature reading to ensure safety. It's a practical application combining these measurement techniques and fundamental laws.
Okay, let's scale this up. The biggest radiation source affecting us is obviously the sun. How does its energy journey through our atmosphere work?
Right. The sun. It's basically this massive nuclear furnace, about 5780 Kelvin at its surface, acting very much like a black body source. The energy intensity that arrives just outside Earth's atmosphere is called the solar constant. It's roughly 1,373 watts per square meter.
That's a lot of energy hitting the top of the atmosphere, but not all of it reaches the ground, right?
No, definitely not. As that sunlight plunges down through the air, it gets weakened or attenuated. Two main things happen: absorption and scattering.
Absorption by what?
By various gases in the atmosphere. Oxygen and especially ozone, O3, are really important because they absorb most of the harmful ultraviolet radiation. Water vapor, H2O, and carbon dioxide, CO2, are strong absorbers too, particularly in the infrared parts of the solar spectrum.
Okay, so gases soak some of it up. What about scattering?
Scattering happens when the electromagnetic waves hit air molecules, or tiny particles like dust or water droplets. They basically get bounced off in different directions.
And the scattering, does it have visible effects?
Oh, absolutely. This is where it gets really neat. The scattering by tiny air molecules, called Rayleigh scattering, is much stronger for shorter wavelengths, blue and violet light, than for longer wavelengths like red light.
So that's why the sky is blue.
That's exactly why the sky is blue. The blue light from the sun gets scattered all over the sky by the air molecules, making the whole sky appear blue to us.
And sunsets, why are they red?
Same principle. When the sun is low on the horizon at sunrise or sunset, its light has to travel through a much thicker slice of atmosphere to reach your eyes. By the time it gets to you, most of the blue light has been scattered away in other directions. What's left, coming straight through, is mostly the longer wavelength reds and oranges.
That's brilliant. Okay, so the sunlight that does make it to the ground, it's a mix.
Yes, we differentiate between direct solar radiation, the rays that come straight from the sun without scattering, casting sharp shadows, and diffuse solar radiation, the light that's been scattered by the atmosphere and seems to come from all parts of the sky. The total solar radiation hitting a surface on the ground is the sum of these two.
This talk of atmosphere absorbing and letting light through, it sounds like we're circling back to the hot par example, the greenhouse effect.
You got it. The greenhouse effect is a perfect example of radiation principles at work, both on a small scale like a car or a literal greenhouse, and on a planetary scale.
How does it work with, say, the glass in a car window?
Okay, think about the properties of glass. Glass is highly transparent to visible light and the near-infrared part of the solar spectrum. roughly zero point 0.3 to 3 micrometers. That's where most of the sun's energy is. So sunlight passes right through the window easily.
Sunshine gets in.
Right. Now, the surfaces inside the car, the seats, the dashboard, they absorb this solar energy and heat up, but they're only at, say, room temperature or a bit hotter. So what kind of radiation do they emit?
Long wavelength infrared.
Exactly. They re-radiate energy, but because they're much cooler than the sun, it's mostly long wavelength infrared radiation, say wavelengths longer than 3 micrometers. Now here's the key. Glass is practically opaque to that long wavelength infrared.
So the heat radiation trying to get back out gets blocked by the glass.
Precisely. The solar energy gets in easily, but the infrared heat radiated by the interior gets trapped, so the temperature inside builds up. That's the greenhouse effect in action.
And this applies to the Earth's atmosphere, too.
Yes, on a global scale, certain gases in our atmosphere, primarily water vapor and carbon dioxide, act like the glass in the greenhouse. They let most of the incoming short-wavelength solar radiation pass through to warm the surface.
Okay.
But they are strong absorbers and emitters of the long-wavelength infrared radiation that the Earth's surface radiates back upwards. They trap some of that outgoing heat, warming the lower atmosphere and the planet's surface.
Which is essential for life,
But increasing the concentration of these greenhouse gases, especially CO2, from burning fossil fuels, enhances this trapping effect, leading to concerns about global warming and climate change. It also explains, by the way, why humid places have less extreme temperature swings between day and night compared to dry deserts.
How so?
The water vapor, the humidity, acts like a blanket, trapping the outgoing infrared radiation at night, keeping things warmer. In a dry desert with clear skies, that infrared radiation escapes much more easily into space, so temperatures plummet after sunset.
Fascinating. So, knowing all this, can we actually design surfaces specifically to control how they interact with solar and infrared radiation? To make things hot or keep them cool on purpose?
Absolutely. This is the whole field of selective surfaces. The key idea is that for many applications, especially involving sunlight, we don't want surfaces to behave like gray objects with properties the same at all wavelengths. We want them to be non-gray or selective.
Meaning they have different properties for solar radiation versus infrared radiation?
Exactly. Take a solar collector, like for heating water. What do you want it to do?
You want it to absorb as much sunlight as possible.
Right, so you need a high solar absorptivity. But once it gets hot, you don't want it to lose that heat by radiating it away.
So you need low emission in the infrared.
Precisely. You want a low thermal emissivity. So the ideal solar collector surface has high ons and low A. We look for materials with a high ISOR ratio. Something like clean galvanized sheet metal can have a ratio around 5.
Okay. What about the opposite? Keeping something cool, like a building roof in a hot climate.
Then you want the reverse. You want to reflect as much sunlight as possible, so you need low solar absorptivity, and you want it to efficiently radiate away any heat it does absorb, so you need high thermal emissivity.
So now you want a low ISOR ratio.
Exactly. Anodized aluminum, for instance, has a ratio around 0.17. White paint is a common example. It reflects sunlight well, low AS, and emits infrared well, high NE. Choosing the right surface properties can make a massive difference in how much heat an object gains or loses, especially under the sun.
It really highlights how we can engineer interactions with radiation. And it connects to renewable energy too, right?
Definitely. When you think about it, most forms of renewable energy, hydroelectric, from rain cycles, wind from atmospheric pressure differences, even biomass, they are all ultimately driven by the energy input from solar radiation. It's the prime mover.
That's a great perspective. Okay, let's zoom back into something very concrete. Windows. We know they let light in, but how do they factor into a building's heat balance?
Windows are huge players in building energy use. They let in solar heat, but they can also be a major source of heat loss in winter and heat gain in summer through conduction and radiation.
How do we measure the solar part specifically?
The key metric is the solar heat gain coefficient, SHGC. It's a number between 0 and 1 that tells you what fraction of the incoming solar radiation actually ends up adding heat to the inside of the building, considering both what's transmitted directly and what's absorbed by the glass and then re-radiated or convected inwards.
So a lower SHGC means less solar heat gain.
Exactly. Sometimes you'll also see a shading coefficient, SC, which basically compares the window's SHGC to that of a standard piece of clear glass from decades ago. A lower SC also means less solar gain.
If I want to reduce that solar heat gain, say in summer, what are my options besides getting low SHGC windows?
Shading is critical, and here's a key takeaway.
Yeah.
External shading is much, much more effective than internal shading.
Like overhangs or awnings.
Yes. A well-designed roof overhang can block the high-angle summer sun entirely, stopping the heat before it even hits the glass. But it can still allow the low-angle winter sun to come in underneath and provide passive heating when you want it.
Clever. What about inside shades like blinds or curtains?
They help, but mostly by reflecting some of the solar radiation that has already passed through the glass back outwards. Light-colored, tightly woven fabrics work best for reflecting, but the heat has already entered the building envelope to some extent.
Okay, external shading first. Now, what about those special low-E windows? You hear that term a lot. What do they do?
Low emissivity, or low coatings, are a fantastic technology. They are microscopically thin, virtually invisible, metallic or metal oxide layers applied usually to one of the internal surfaces of a double or triple glazed window unit.
And low emissivity means?
It means the surface is a very poor emitter of long wavelength infrared radiation. Remember, shiny metals have low emissivity.
Okay, so how does that help?
Think about winter. Your warm room is radiating heat towards the cold window. The low-E coating on the inner pane facing the room reflects that heat back into the room, significantly reducing heat loss by radiation.
Keeps the heat in. What about summer?
In summer, if the window itself gets hot from the sun, the low-E coating on the other inner pane, facing the outside, prevents that heat from being radiated into your cooler room. It keeps unwanted heat out.
So it works both ways, winter and summer.
Yes, it reduces heat transfer by radiation in both directions, improving comfort and saving energy year-round. The specific design and placement of the coating can be optimized for different climates. Cold climates want to maximize passive solar gain in winter while minimizing heat loss, high SHGC, low U factor thanks to low E. Warm climates want to minimize solar gain year-round while still allowing visible light, low SHGC, low U factor.
It's amazing how much physics goes into just a window, and the energy savings can be significant.
Absolutely. Installing something simple like a reflective window film or upgrading to modern low windows can often pay for itself in energy savings within just a few years, especially in climates with high heating or cooling costs. Plus, the improvement in comfort is immediate. Hashtag outro.
Wow, what a journey through thermal radiation. We started with how it's fundamentally different, needing no medium, explored the ideal black body and the laws governing its emissions, Stefan Boltzmann, Planck, Wien.
Then unpack the properties of real surfaces, emissivity, absorptivity, reflectivity, transmissivity, and how Kirchhoff's law ties them together.
And we saw its huge impact on our world, from the sun's energy reaching Earth, scattering to make the sky blue, the critical role of the greenhouse effect, both naturally and concerningly.
And finally, how we harness these principles to design selective surfaces for solar collectors or cool roofs, and engineer sophisticated windows with low coatings to make our buildings more comfortable and efficient.
It really feels like these nuggets of knowledge, as you called them, give you a new lens to see the world. Understanding why things have color, why old light bulbs were so hot, how that car gets so warm.
It demystifies a lot of everyday phenomena and also highlights the incredible ingenuity behind technologies we might take for granted, like energy-efficient building design.
So thinking about all this, what does it mean for you, our listener? Maybe next time you choose curtains, you'll think about reflectivity. Or perhaps planning a trip, you'll consider how humidity affects nighttime temperatures differently in various climates, all thanks to infrared radiation.
Or maybe even bigger picture, how understanding these fundamental ways heat moves allows us to design smarter cities, more efficient energy systems, and ultimately perhaps build a more sustainable relationship with the energy flows that shape our planet. Something to think about.